All right. Hey, everyone. Welcome. Good afternoon. My name is Gabor Szauer. I'm a developer relations engineer here at Oculus. And what I do is I help developers like you succeed in our ecosystem by providing technical guidance, insights, and just in general helping optimize your games. I started at Oculus about a year and a half ago. And on my very first day at Oculus, my manager puts a prototype Zero Quest on my desk, gives me the access to the source code of a Rift game, and says, hey, can we port this to Quest? And we did. And since then, we've ported a couple of titles over. And today, I'm here to share some of the learnings we've had from doing these ports. So we have a lot to cover and not a lot of time. But good news is I talk pretty fast, so I think we'll have plenty of time for Q&A after. So we're going to talk about some design considerations, some like technical art side porting considerations, some really deep technical things you're going to need to actually port. And then we'll talk a little bit about how to profile your games and make sure that you actually hit frame rate. So let's start with some design considerations for standalone here. And the first thing I want to say here is there is no secret sauce. There's no super secret SDK or anything. Everything you need to develop for the Quest is available on our website today. If you're using a fairly recent engine, fairly recent integrations for the engine, it should work just like a Rift with touch, same API, same design, same everything. The big and most obvious difference is the cameras, where with the Rift you have 2 cameras looking at you. With the Quest you have 4 cameras on your face. Now, this doesn't sound like a big deal, but you have to keep in mind your field of view is not infinite. It's actually attached to your face. There is some more obvious design considerations, like if you reach behind your head to grab something, you're going to lose your controllers. Those are actually not too bad. If you only lose your controller tracking for a second or two, you can usually fake it pretty easily. But some of the situations you get into aren't so obvious. Like, let's say I have 2 guns, and there's a really, really loud sound coming from my right, so I look over. All of a sudden, my left hand just left the field of view. So some of your environmental cues might actually cause you to look away from your controllers and lose tracking. For the most part, that's not going to be an issue, but it is something to keep in mind. Speaking of controllers, these are the touch controllers that ship with Oculus Quest. Same button layouts, same everything as you see on a Rift touch controller. The big difference is that the rings are flipped upside down, which at first doesn't seem like a big deal, but that also has a couple of design considerations. For example, if I'm holding out my left controller because I have a watch menu open and then I use my right controller to poke at it, all of a sudden I'm occluding the tracking rings and I lost tracking. Very similar to holding a gun up or potentially drawing a bow back. There's a lot of situations where you can potentially lose tracking. And most of these situations aren't going to be an issue if you know they're going to happen and you plan accordingly. That's all I really had to say on design considerations. Let's talk about actually what it takes to port to Quest. And when I first put this talk together, I wanted to come up here and I wanted to tell you, hey, in our ports, we've seen the average number of draw calls be X and the average number of triangles be Y. But those aren't really good metrics, right? Because you can have 2 games, same number of draw calls, same number of triangles, and the games behave very differently because a lot of the cost of a draw call depends on your current GPU state. So instead, I figured let's take a look at what makes a draw call expensive potentially. These tests were done in Unity, by the way. So the biggest impact on performance for a draw call is going to be changing materials. There's a lot of state that needs to be rebound, a lot of state that needs to be changed. So you want to avoid changing materials as much as possible, draw things with the same material as much as possible. Second biggest cost, changing meshes. This is going to go into actually merging meshes, right? You can merge most of your static meshes, so you can actually avoid changing meshes. There's a couple things that don't really impact the draw call, like texture size. Or even texture filtering. So if you can, try to use trilinear filtering. It looks the best. It's what we kind of suggest to use. It's probably what you should be doing. Also, mesh size doesn't matter, right? So it doesn't make a huge difference if you're sending a mesh that's just between draw calls. It doesn't make a huge difference between draw calls if you're sending a mesh that's smaller versus a mesh that's larger. And we'll see what this means practically in just a little bit here. A little bit of a surprise, although it shouldn't really be too much of a surprise, texture compression makes a huge difference, right? The hardware has hardware texture compression supported, and if you can use compressed textures, you should. It's going to keep the bus to the memory less noisy, and it's going to have a huge impact on performance. So all of that sounds great, but it's not immediately obvious how that translates into making an actual game. So we're going to take a look at what the Dead and Buried team did to port their game over and what these numbers actually meant for them. So first, the most obvious thing is to bake your lighting, right? On a Rift, you might have real-time shadows everywhere. You might have some like volumetric lights, some nifty effects. On the Quest here, we have all the lighting baked into the scene. In case it's not obvious, the right side's Rift, the left side's Quest. What might not be immediately obvious here, though, is the actual difference between the complexity of the scene, right? So on the Rift, we have like 700,000 polygons and over 1,000 draw calls. On the Quest, we reduced the polygons significantly, and it's only 33 draw calls, which makes this scene super cheap to render. And we'll go into detail on how this was achieved in just a second here. So the big thing is merging your objects, right? So on the Rift, you have like 915 objects that make up the saloon. On the Quest, you only have 2. And this goes back to changing meshes being expensive, sending bigger meshes to the GPU at a time being less expensive, right? So you merge your objects, you send these big meshes over instead of the small ones. That's going to be a pretty good performance win. So why 2 objects and not just 1? Well, you want to avoid overdraw if possible, so it does help to have a couple extra objects so they can be called, or so the objects that are closest to you can be drawn first. Some GPUs will do Z sorting for you. The one in the Quest doesn't. So if you can submit close geometry first, it's going to be a bit of a win. Texture compression. I can't really tell the difference between these 2 textures. And if we zoom in super close, you can kind of tell where the compressed texture gets jaggy around the edge of the material. But where we can't really tell, the GPU can most certainly tell. You know, you have 20 megabytes of uncompressed data or just a megabyte of compressed data. ASTC texture compression is recommended for most of your 3D models here. So you've merged your meshes. You have compressed your textures. You want to reduce your materials. And the best way to do that is going to be to actually atlas your textures, right? Your merged meshes should just reference one texture atlas. That way you can do the whole mesh in just one draw call. Less draw calls, bigger meshes, less data to send to the GPU, faster your game's going to be. So a quick example of how we actually simplified materials and assets for some of the game assets in Dead and Buried. This is the Hellsinger revolver, right? On the Rift, it's 5 textures, something like 6,000 polygons. On the Quest, it's only 1 texture and like only 30 polygons, 33. Similarly, most of the scenery is also reduced in complexity, right? On the Rift, you have this piano, which is 3 textures, 2,000 polygons. On the Quest, it's just 1 texture, 670 polygons. And this is kind of a trend you see in all the assets when we're doing these ports, right? Less textures, fewer polygons, preferably just 1 material, so the whole thing can just render in 1 draw call. So this sounds a little bit restrictive. This sounds like, hey, maybe the application isn't going to look the same or similar enough. I think it will. So let's take a look at a video of what these 2 games look like side by side. Pew, 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 pew. Pretty close, right? Pretty good. Right on. So you've simplified your materials, you've reduced the size of your meshes, you've made everything be 1 draw call, your game is super awesome, it's running very performant, but you want to make it look really, really good, right? And that's often going to mean adding some kind of post-processing effects, adding some kind of interesting rendering effects. You can do a lot of really interesting effects, but you kind of have to understand the GPU that's in the device, right? It's not the same as a PC class GPU. It works a little bit differently. And understanding how like a tile-rendered GPU works is actually very important here. So how does a tile-rendered GPU work? Well, you have a little bit of very fast cache memory on the GPU itself. We're going to call this a tile. And then you have a lot of system memory, right? The problem with system memory is it's far away from the GPU, so it actually takes a decent amount of time to access, to read to and write from. Tile memory isn't big enough to hold your whole frame buffer. So your actual frame buffer is stored in system memory. And what the GPU has to do is render into the tile and then copy over to the actual frame buffer. So you've submitted all of your draw calls. The GPU does this thing called binning, where it sorts what triangle affects which tile in the frame buffer, so it knows what tile to draw stuff into. And then it proceeds to draw your frame buffer. It has to draw the left and right eye separately, even if you're using an extension like multi-view. Multi-view is more of a CPU side win because you reduce the number of draw calls. But it still has to do those twice, one for each eye, right? So for every eye, you're going to draw a little bit into the tile memory, and then you're going to copy that over to the frame buffer. I'm going to repeat, draw, copy. So each of these copies is called a resolve. So whenever you hear like the cost of a resolve, that just means the cost of copying data from the fast GPU cache to the larger system RAM, right? Copying from the system RAM back to the GPU cache, that would be an unresolved, and those are really, really expensive, and you want to avoid doing those as much as possible. So the GPU just kind of chugs along, does its thing, renders one tile at a time, resolves it into system memory. Once all tiles have been rendered and resolved, this particular scene is then ready to be presented. So the important thing to know about this whole render, resolve, render, resolve, render, resolve process is that only color is ever actually resolved, right? So depth information, for example, isn't actually copied out of the tiler. And because of this, the size of your tiles don't really matter. It doesn't matter if your tile is tiny, like 200 by 200 pixels, or large, like 500 by 500 pixels. And just as an example, let's actually go through and do the math for this, right? So we're going to figure out the size of a pixel in bits, right? So we have two examples. We're going to call example 1 a full pixel, example 2 a minimal pixel, right? Your full pixel has 32 bits for color, 8-bit stencil, 24 bits for depth, 4x MSAA. Pretty common for a game. Your minimal pixel just has a color component, 32 bits, right? So your full pixel is 256 bits. Your minimal pixel is only like 32 bits, right? So since tile memory is limited, like it's a finite space of memory, the more memory a single pixel takes, the less amount of pixels you can fit into a tile, right? So how many pixels can we fit into a tile? Okay, there we go. In order to know that, we have to kind of know how big a tile is. So let's assume it's around 8,000 bytes. That's a fairly sane assumption, right? So when we're looking at a full pixel, that's about 32,000 pixels per tile. When we're looking at a minimal pixel, that's about 250,000 pixels per tile. 32,000, 250,000, sounds like a lot of pixels. But when you actually divide out what the size of each of those tiles are, it's actually pretty small. So for your full pixel, each tile is like 160 by 200. For your minimal pixel, each tile is like 500 by 540, right? So the next logical question is, how many of these tiles do I need to render to resolve a full frame buffer? Well, your average drawing surface, your default frame buffer size is 1280 by 1280, which is about 1.5 million pixels, a little more. Luckily, I only have 2 eyes, so we only got to draw this like twice, which leaves us with a little over 3 million pixels, right? So if we divide this by the size of the actual number of pixels in a tile, for the full pixel, we get around 51 tiles. For the minimal pixel, we get around 6 tiles. So the question is, what's faster to resolve, right? Is it 51 tiles, or is it 6 tiles? And that's a trick question, because they take the same amount of time to resolve. It doesn't matter how many tiles you have, because you're literally just copying memory. You're copying bits. So what matters is what you're copying bits into. In this example, we're copying bits into an RGBA32 target, which means the resolve for both of these is going to be about 1 millisecond. So quick recap on what's important here, right? Depth is not copied out of the tiler. if you want access to your depth information, you're going to have to write 1/depth into your alpha channel. MSAA doesn't actually leave the tiler, right? It doesn't work like it does on a PC. You don't have an MSAA texture. So this actually makes 4x MSAA a lot cheaper than what you would find on a PC, right? Almost free. I mean, if you're like fragment bound, it's not going to be free, but it's considerably cheaper, and you should definitely try using 4x MSAA. And then the big takeaway, and the thing to really keep in mind, is that the cost of a resolve is directly proportional to the target that you're resolving into, the target of your frame buffer. So again, this is some high-level information, but how do you actually apply it to like an actual game, right? And the big takeaway is you want to avoid extra resolves, right? If you can move everything into your first forward pass and you can just have that one resolve, your performance is going to be considerably better than if you were to have multiple resolves. So first, we have an example like volumetric lights or light rates. These are pretty easy to fake, actually, with imposter geometry. You just have some quads in the scene with some light rate texture on them. You have maybe some particles playing at the bottom of it, and it looks fairly convincing. If you want to do real-time shadows, there's no way to avoid that additional resolve, but so long as you only have like one shadow casting light, it's a directional light, your shadows are hard shadows, even if they are like a rather high resolution, they should work just fine. You might see a little jaggies near the edge, but you have to really look to see those. If you want to avoid having the additional pass, you can do something like potentially planar shadows or blob shadows. Those look fairly convincing too. Slightly more expensive effect, something that you'd normally do with a second pass on a PC, would be something like color grading, right? So on a platform like the Quest, you can actually do color grading per material. And what this means is you have to take something like a color lookup texture and a screenshot of your game. You import both of these into Photoshop, and you play with your color curves until you find the look you're looking for. Then you export your lookup texture from Photoshop, and you pass it into every material of your game. And the last step of your fragment shader is going to be to do the color lookup on this actual lookup texture. That sounds like a considerable amount of work, right? Like changing all of your materials, changing all of your fragment shaders, like considerable amount of work. But it's actually not, because in this scene, for example, the entire saloon only takes 2 draw calls. Those draw calls share one material. Each zombie has its own material, but they all have the same shader. I had to edit 2 shaders and 8 materials to add color grading to this screenshot from Dead and Buried. So a slightly more advanced effect here would be HDR rendering, which I didn't actually do. There's a good reason for it, though, I promise. So to kind of understand why, we have to examine how a typical HDR effect is actually rendered, right? Normally, your HDR is done in 2 passes. First, you render your scene into a floating point buffer, which is 64 bits per pixel, high resolution. Then you do some kind of full screen tone mapping pass, right? And that tends to be like 32 bits per pixel. So right there, you have 2 passes. That's an additional resolve. That should kind of sound a little performance heavy. But when we actually look at what's happening, remember, the cost of your resolve is proportional to what you're resolving into. So resolving into that 64 bits per pixel target is going to be twice as expensive as your normal 32-bit resolve. So all in all, in this scene, you're resolving 96 bits instead of just 32. Your resolve time, and resolve time alone, goes from 1 millisecond to 3 milliseconds. On top of that, you still have to do all of the work that the shaders would be doing. You still have to do sort and batch the geometry for each of those draw calls potentially. So it's actually not uncommon for an effect like this to take 5 to 6 milliseconds. And that's fairly expensive when you consider that Quest runs at 72 frames per second and your frame time is 13.8 milliseconds. On top of that, HDR rendering really mostly looks good when you have dynamic lights in the scene, and if you've baked most of your lights, it's not going to look great, so it's not really worth the effort a lot of the time. All right, so let's talk a little bit about profiling, and this is my personal profiling workflow when I tackle porting something to Quest. You don't have the same kind of profiling tools that you have on PC, right? Like on a PC, it's not uncommon to start a query timer on the GPU, render something, stop the query timer, and see how many milliseconds that took, see what the effect of those draw calls are. You can't do that on Quest because it's a tiled GPU, right? So before you can see how expensive a draw call was, you have to wait for all the tiles that draw call touches to resolve. So your actual timing is going to be off. The tools work a little different, and you have to do a little more manual debugging here. So the first question you need to ask yourself is, am I CPU or am I GPU bound? Luckily, figuring that out is actually pretty simple. Just don't render anything. Just stop rendering. Disable your camera component, stop submitting draw calls, just don't render anything, right? If you stop rendering and your performance improves, you were GPU bound. If you stop rendering and your performance did not improve, you're CPU bound. So being CPU bound, you have to use some kind of an instrumented profiler to find where your actual hotspots in your code are. We provide Oculus Remote Monitor tool where you can kind of set events in your code and see a video stream on the top at the same time to kind of correlate where and why your performance is dropping. And all engines provide their own profilers. Unreal Profile is really good if you're CPU bound, so is Unity Profile. On the other hand, if you're GPU bound, it's a little more complicated, because you now have to figure out, am I fragment bound or am I vertex bound? Figuring that out, though, is easy too. All you have to do is just resize your actual render target, what you're rendering into. Something small, like, say, 0.01%. And the idea here is you're filling less fragments, you're doing less fragment work, right? So if you've resized your target and your performance did not improve, you were vertex bound. If you've resized your render target to something small and your performance did improve, you were fill bound. If you're fill bound, your best friend is going to be Snapdragon Profiler. You can get some pretty in-depth system traces, see what's happening on the GPU down to the tile level. You can also do frame captures and do frame analysis here. Another great tool that we have support for is RenderDoc. And there is actually a talk today reinforcing mobile performance with RenderDoc at 3:30. It's a classroom session by Remy. I highly suggest going to it. The cool thing about RenderDoc is you can actually take a RenderDoc trace on any device and play it back on any compatible device. So you're not limited to just debugging on the Quest, even if you did capture the actual frame profile data on a Quest. So on the other hand, if you're vertex bound, there's a couple things you can do here, right? First thing is, and the most obvious thing, is to reduce the number of vertices you have, right? To make your meshes smaller. You can also LOD pretty aggressively. Use imposter geometry when possible. And if you're using imposter geometry, you probably want to avoid alpha clip. One of the cool things that Emburied does is they actually place several points throughout the playable parts of the arena, and they render the whole scene into a cube map from each of those points. But what they actually render is the triangle ID for every triangle. And any triangle that isn't seen from those renders gets called out of the game. And they get something like a 30–40% reduction in the number of triangles they have. So quick recap here. This is Gabor's flowchart for what to optimize. And it's an iterative process, right? You're going to find your biggest, most expensive bottleneck. You're going to fix it, and the next one shows up, right? Something's always going to be the most expensive thing. You want to iteratively keep doing this until you're running at frame rate and you're good to go. All right, recap. Developing for the Quest, most of the work you're going to do is going to be technical art. It's going to be reducing number of triangles, batching meshes efficiently, atlasing your textures efficiently. On top of that, any additional things you want to do, like special effects or like just any kind of fancy rendering, you're probably going to want to be pretty intimate with the GPU and understand exactly how it works. But when you make an application for the Quest, if you keep these things in mind and you build with performance in mind, you can get some really, really unique experiences. This is the first device that's inside out, fully tracked, full hand presence, without any wires at all. So good news is I talked really fast like I said I would, and we have a little extra time for Q&A here, so I'll be taking questions, comments, rude remarks, whatever you've got.